rather than subdividing our area into rectangles, why don't we use trapezoids? Take a look at the diagram here. We've got our function, and we have a partition of our function into 4 subintervals. And if I use both the right endpoint and the left endpoint, just connect them, it does make a trapezoid right there. And look how good of an approximation that is. Sure, we have a little bit, not enough here. We got a little bit too much here, a little bit too much here, but it's certainly closer than the left Riemann sum and the right Riemann sum individually. But you know what? The trapezoid is basically the average of the left and the right Riemann sums. To see that, let's take a look at this. Follow this logic, if you will. So in order to understand this, we have to know what the area formula is for a trapezoid. So remember that that is equal to 1/2 sum of the two bases, b1 plus b2, and then you multiply it times your height. So let's see if we can apply that to this diagram here. This is just looking at the very first trapezoid, and then you can generalize it to all the rest of them. Okay, so as a trapezoid, we have to be able to identify what are the bases and what's the height. So a lot of people might think that this right here is the height, which is what it was when we were talking about the rectangle. But for a trapezoid, the height is the distance between the two bases. And for us, that's going to be down here. It's the width of the subinterval, right? It's the distance between these two parallel bases, and the two parallel bases are actually our function values. And those function values are going to be our b1 and our b2. So let's put all of that stuff together in order to find the area of this very first trapezoid. Using that area formula, substituting for b1 is going to be our f of x sub 0. That's our left endpoint plugged into our function. Our b sub 2 is going to be f of x sub 1. That's our right endpoint plugged into our function. And this height that's right there is the width. And our width, since it's a regular partition, we would use b minus a divided by n. There you go. All right, just for simplicity's sake, I'm going to take this b minus a and divided by n and just replace it with a delta x. And let's see what would happen if we take this delta x here and then just distribute it through the parentheses using some good old distributive property like this. Now, when it's written like this, we can see that what we have is 1/2 of the sum of two things. That's an average. This thing that's on the left-hand side, I'm using a left endpoint multiplied times the width. That's going to be the left Riemann sum. And here I'm using a right endpoint multiplied times the width of the subinterval. That's going to be a right Riemann sum. And of course, this is just the first trapezoid, but you would continue this with each individual trapezoid, and you would find that the area of the trapezoid sum is the average of the left and the right Riemann sums. And that's exactly how we'll tackle it when we examine. Whoa, oh yeah, don't let me forget. Here's a picture that summarizes this. So you have in blue here, you have the left Riemann sum. In green here, you have the right Riemann sum using the right endpoint, and then the average of those two things is the trapezoid sum. So again, we're going to apply that thing here on example 3 when we look at it again, but this time in the context of summing up some trapezoids. Now, one of the things that we could do is use our two answers that we had before, the left and the right, add them up, divide by 2, find the average, but what fun would that be? None. Instead, let's see if we can kind of generalize this thusly. Our area should be approximately equal to, there we go, the summation from I is equal to 1 to 4, and we're taking the average of the left and the right, so I'm going to take 1/2 of, and in parentheses here, let's write the summation for like the left Riemann sum and the right Riemann sum. So I need a function value, and for the left side, I think it was f of I minus 1 divided by 4, and then we would multiply that times its width, and its width was a fourth, plus f of the right Riemann sum was just simply I over 4, also multiplied times its width of 1/4. And there you go. All right, so notice that you have in common here 1/4. We can take those 1/4, so we could factor it out, multiply it times this 1/2 that's right there, and get 1/8. 1/8, and then in parentheses, f I minus 1 over 4 plus f I over 4. Whoop. All right, so this is all of the function values evaluated at the left endpoints, all the function values evaluated at the right endpoints. Okay, so what would this summation look expanded out? We would have 1/8 on the outside of all of this, and then on the inside, our first, let's see, our first left endpoint was f of 0, and we can get that by just plugging in 1 here. So 1 minus 1 is 0 divided by 4, it would be f of 0, right? And then continue to do that for each one of these all the way up to 4, and we knew that was plus f of 1/4, f of 2/4, f of 3/4. And that would be all of the left endpoints. But now you have to add in all the right endpoints. So if I stuck in 1 in for this I here, I would have f of 1/4. And notice that that perfectly lines up with this f of 1/4. If I stuck in a 2 here, I increase that by 1. It would be 2 over 4, which lines up with this one. And then we would also have f of 3/4 when we stick in 3. And one more, we'd have f of 4/4. Now, the whole entire reason I did this is to expose you to this thing called the trapezoid rule. Whenever you have a regular partition, you have some sort of function and trapezoid rule, you always have one of the first endpoint, and that's this guy right here. And notice that you have two of all of the interior ones, 2f of 1/4 plus 2f of 2/4 plus 2f of 3/4. And then you have one of the right endpoint. That should be 4/4. What a mess. Okay, so it always follows that pattern of 1, 2, 2. Oh my gosh, I didn't put my 2. Nobody screamed at me. Maybe you did, and I just didn't hear you. Because you screamed too quietly. Okay, anyway, so it's 1, 2, 2, 2, 1. It's always that kind of pattern for this thing that's called the trapezoid rule. All right, but you know, honestly, for this particular answer, you would just plug in all of these things into your function, add them all up, or do what we suggested at the very beginning of this example. You just take the average of the left, you take the average of the left and the right here, and for the trapezoid, you should get 0.34375. I hope that's right. Okay, well here, let's just take a look at this table that summarizes all of these things. So in this table, we have the left Riemann sum, the right Riemann sum from, let's say, subintervals of 10, 20, 30, 50, 100, and 1,000. This next column here is the midpoint sum and then the trapezoid sum. So take a look at all of those numbers. Think in terms of a limit here. Are they approaching anything in particular? Look at the numbers that are down there. It looks sort of like it's approaching 1/3. In the next example, in the next video, we will prove that it is in fact exactly 1/3.